We've mentioned a little bit about UDP and TCP. Let's go into some detail about how TCP works. We know there are two main transport protocols in the internet, UDP and TCP. There are others. The third one is SCTP, and there are some other extensions as well, DCCP as well. And there are other transport protocols which are not so common but used for very specific purposes, like over a satellite link. But the two main ones, TCP and UDP. TCP provides reliable delivery of data, UDP unreliable delivery. We're going to spend some time looking at one aspect of TCP, one part that we haven't studied before, that we didn't study last semester, mainly congestion control. And see how TCP impacts on the performance of our applications. In your assignment in phase 2, you're studying just UDP, because UDP doesn't impact on the performance of applications so much. So it's a good measure of the raw performance. But we'll find that TCP does impact on the performance of applications, and in phase 3 of your assignment, you'll investigate how that does it. A quick review of TCP, what we know about it, and then we're going to go into detail how congestion is caused in the internet and how TCP copes with that. So how TCP implements congestion control. And we'll finish on a few issues about, or other issues about performance, mention them. Last semester in ITS413 we introduced TCP. Let's recap on some things we know. It's the most commonly used transport protocol today, so most of the applications you can think of probably use TCP. Web browser, your email client creates TCP connections, secure shell. Most or many audio and video applications still use TCP for data transfer. Some will use UDP. Some voice call applications will use UDP, others will use TCP. So TCP is commonly used in most applications because many applications we care about reliability. I want to send data. The data that I send, or the other way, the data that I receive should be identical to the data that I send. And that's what TCP provides for us. It provides a reliable stream-oriented transport service. A stream means that when the application delivers data to TCP, TCP doesn't treat it as different messages, it treats it as a sequence of bytes, a stream of bytes. I'll draw our stack just as a reminder. Our 5-layer stack, we have our application or application protocol, generate data. Transport layer, we're focusing on TCP. IP is the network layer, and whatever the data link and physical layer are at the bottom in general. The application generates data at the source, sends it to TCP. So the application may send data to TCP at different times. So we create a connection from source to destination computer, and then let's say at the start of the connection the application delivers 1,000 bytes of data, sends it to TCP. That needs to be sent. And then 1 second later it delivers another 500 bytes of data, sends to TCP. At time equal to 0 and at time equal to 1. That's when the application generates data. It depends on what the application is and what the user is doing as to what happens here. From TCP perspective, it doesn't necessarily treat these as two different messages. From TCP's perspective, This is just a stream of bytes. 1,500 bytes. It doesn't distinguish that there are two messages there. It may send them all in one TCP segment across the internet, like shown here. That is, join them together. Or it may send them as two segments of 1,500 bytes, or multiple segments. In this example, 3 segments of 500 bytes each. It doesn't care what the application delivers. It's just a sequence of 1,500 bytes. Send it the best way possible across the internet. The best way possible is defined by the algorithms in TCP. So it's a stream-oriented service. It's just a stream of bytes. And as a result, the receiving TCP, and that's worth illustrating, the receiving TCP does not distinguish between the messages either. So those, for example, application generated 1,000, what did I write, 100? 1,000 bytes. And then sometime later 500 bytes, sends them to TCP. TCP decides in this example to send 3 TCP segments across the internet, each of 500 bytes. They are sent across the internet, segment 1, 2 and 3. They are received. Physical layer, data link layer. IP receives 3 IP datagrams, 1, 2 and 3, sends them to TCP. And here's our receiving application on the other side of the internet. It receives 3 segments here, each of 500 bytes. Depending on when it receives them, it may send, again, just a sequence of bytes to the application. It could send 1,500 bytes to the application. It doesn't put it back necessarily into this separation of 1,000 bytes and 500 bytes. So really, from the application's point of view and interfacing with TCP, application sends bytes to TCP, TCP delivers them. Sending 1,000 and then 500 bytes makes no difference from TCP's perspective. The way that's done is using a buffer. When we say the application sends to TCP, it just puts in memory in some buffer. TCP takes it out of the buffer when it's ready to send, and TCP chooses how much to send, not based on what the application put in the buffer. So once this 1,000 bytes is in the buffer, and then the other 500 bytes, there's no distinguishing between those two messages. And the same at the receiver. The receiver takes the received segments, puts them into a buffer. The application reads that buffer. So it's up to the application to control how it interprets what's received. So that's a stream-oriented service. And related to that, it's buffered transfer. When does TCP send this data? Again, the data may be buffered, stored in the buffer so for some time before it's sent. The application doesn't control that. It just puts it into the buffer. TCP decides when to send. And same at the receiver. TCP may put 1,000 bytes in the buffer. It's up to the application to read from the buffer and take it out. So it's buffered transfer. There are some options to force the transmission of the data. That is, the application uses an option to say, let's put 1,000 bytes in the buffer and force TCP to try to send that, instead of waiting for further data in the buffer. Using a buffer transfer is useful if we want efficiency if the application is putting a small amount into the buffer. Application puts 10 bytes in the buffer. If TCP sends that in one segment, that could be very inefficient because there's a large header. So instead of sending 10 bytes at a time, TCP may wait until it receives a large amount of data in the buffer and send it all in one segment. So that's the benefit of the buffered transfer. We know TCP is connection oriented. Before we send any data, we set up a connection. SYN, SYNAC, ACK is the basic approach. And we use that to maintain our sequence numbers and other information. Full duplex connection, although we'll show sending data in one direction, we can actually send back in the opposite direction as well. And provides reliability. Send data, receiver sends back ACKs to indicate that we've received it okay.
Can two application data are in the same TCP segment?
No. They're two different connections. That is, if I have on my computer two applications, yes, we separate the data between different applications. That is, application 1 and application 2. Those applications would be assigned different port numbers. So port number of your web browser, port number of your email client, and therefore we'd set up two different connections, even if it's to the same destination computer. Two different connections, so the data is treated separately in that case. TCP, you can think TCP is running twice in that case, one on each set of data. Where is the packet put back in order? It's not. I'll put back in order if they arrive out of order at TCP. So let's say we send these as 3 segments, segment 1, 2 and 3. They're sent across the internet. We receive segment 2, 1 and 3 at the receiver. We receive them out of order. TCP will put them back in order when it puts it in the buffer. That is, it will put this one first, and then that one, and then the third one. So yes, TCP reorders at the receiver. We need sequence numbers for that to work effectively. And the acknowledgement mechanism, we send ACKs based upon the successful receipt of data. We send back acknowledgements. And again, it's not as simple as one data segment, one ACK. We can send the ACKs acknowledge bytes, not segments. So I can send 3 segments containing a total of 1,500 bytes. I may receive one ACK that acknowledges all 3 segments, that is all 1,500 bytes. So although we have acknowledgements, they acknowledge the data, the bytes that are received, not necessarily the segments that are received. And if we don't receive an acknowledgement, we have retransmission mechanisms. We know that will impact on performance of our application. If we have packets lost in the internet between source and destination, there need to be retransmissions, and that's going to reduce our throughput. That's one reason we're not using TCP in our initial tests, because that will impact upon our throughput. You can try TCP with iPerf and see how it compares with UDP. You will try that in phase 3 of your assignment. For reference, TCP segment, we include the port numbers, the header default size is 20 bytes, sequence number to indicate the data being sent, ACK number, and note that we only have one format of TCP segment. There's only one type of TCP segment. There's not a separate header for an ACK. There's not separate for data. They're all just in one segment. A segment can contain data and an acknowledgement at the same time. We send data from source, or from A to B. that data segment can include a flag that says it's also an ACK, acknowledging data that came from B to A. So we have this piggybacking option. So we can also include an acknowledgement number. If the ACK flag is set, the acknowledgement number is red. The window is another parameter or another header field that is useful, and that's used in the flow control. We may refer back to the TCP segment structure during the later slides. Just a description of those fields. And the fact, and again we've covered this before, or at least last semester, that flags are used to indicate that the feature used in this segment, the functionality. If the ACK flag is set, that 1-bit value is set to 1, then that means this segment carries an ACK. So you can have piggybacking of different features. One thing I tend to forget in lectures is getting attendance, so now's a good time to sign your name. Sign your own name, not someone else's. So the main features of TCP, we set up connections. We've studied connection management before. We haven't really studied how we close connections too much. There are different ways to open and close connections, but we know we set up a connection, transfer our data, and then at the end close the connection. In this topic, we're concerned more about the data transfer, not setting up and closing connections. Once we have a connection established, there are 3 main features that are going to impact on performance. Really 3 different sets of algorithms. The retransmission scheme, flow control, and congestion control. Retransmission or reliability, send our data, acknowledge. And there are algorithms to say when to send the acknowledgements. Flow control, what's flow control? Yes, flow control. We have in the internet we have our source computer and receiver computer. On the other side of the internet, we have a buffer for the data that we receive. Okay, because we have buffered transfer, we have a fixed size of this buffer here. The application reads from the buffer at different times, and it's up to the application. So if our buffer has a maximum size of 10,000 bytes, as we transmit data, we put it into the buffer, and it stays in the buffer until the application reads and takes it out of the buffer. That depends upon the application, and the rate at which the application does it may depend upon different factors, including the speed of the computer. So the speed at which the application is doing something. Maybe the application is in a loop, perform some functionality, read from the buffer. Perform some functions, read from the buffer. If those performing functions takes a long time, there may be a long time between reading from the buffer. If the buffer becomes full, 10,000 bytes maximum size, we have 10,000 bytes in there, and we send more data, what happens to that data received? Where does it go? That's not on the slides. Where does the data go? The buffer is full, we receive more data, where does that data go?
Lost.
It's lost. That is, data arrives at IP, IP sends to TCP, TCP has no more memory to store that data. So that's lost. And if we lose data, then our performance is going to go down because we're going to have to retransmit that data eventually. And retransmission leads to more overheads. We don't want to lose data if we can help it. So flow control, basically, The sender, when it sends back segments, includes a value in the window field here that is an indication of how much space we have in the buffer left. If we have 9,000 bytes in our 10,000 byte buffer, it will send back in the TCP segments a value in the window field that tells the source we have 1,000 bytes space available. The window, the flow control window, is 1,000 bytes. You're not allowed to send me more than 1,000 bytes, because if you did, you'd fill up my buffer and I wouldn't be able to receive those bytes or those segments. So, flow control, we use this window field, which is called the advertise window. The receiver advertises to the sender how much space it has available in the buffer, the advertise window. The sender is not allowed to send any more than the advertise window. The abbreviation for the advertise window is AWND. The advertise window is a parameter stored at the source. So when we send back a segment with the window field in the segment set to 1,000, then the source here will set the advertise window equal to 1,000. So the advertise window is dependent upon what the other host sends to us in the segment, the window field. And that limits, or that's one limit of how much we're allowed to send at a time. So that's flow control. We've studied flow control, the sliding window flow control mechanism, we've studied that, and that's what's used here. That is, as we send data and as we successfully receive, we send acknowledgements, which allows us to send more. As we receive acknowledgements, the window size will grow, allow us to send more because the acknowledgements are indicating we've got more space in the buffer. So TCP implements a sliding window mechanism for flow control. We have retransmission schemes, we've covered them before. The thing that we haven't covered before is congestion control. Flow control is making sure that the sender doesn't overflow the receiver computer. Between the sender and receiver, we have routers. We have the whole internet. Routers, switches, and so on. Congestion control is making sure we don't overflow those nodes in the internet, in particular the routers. Because if I start sending too fast from my host to the router that I'm attached to, which is attached to other routers, this router has some processing ability, some buffer for the data that it receives and then sends on. In fact, there are many computers attached to this router all wanting to send on this output link. Maybe this is my computer, this is the internet service provider router. It has many customers connected in, wanting to send on this output link. If they send too fast, such that the input data to the router is greater than what it can send out, data is going to be stored in the buffer is going to fill up, and eventually packets will be dropped by the router. And we don't want packets to be dropped in TCP. The same with flow control. We don't want segments to be dropped at the receiver. We don't want packets to be dropped at routers. Packets being dropped at routers is referred to as congestion. The internet is congested. So TCP implements a mechanism to control the congestion, try to avoid this situation. And that's our background, our review of TCP. Now we're going to go into the new stuff of how this congestion control works. So everything we've said so far you should know already. What causes congestion in the internet? And then we'll go through how TCP controls or tries to prevent congestion. So when we talk about congestion in the internet, normally we're referring to the routers in between the source and destination. Congestion occurs in some network in general if the packets being transmitted through that network, going into it and through it, approaches the capacity of that network, the maximum number of packets it can send. We here refer to packets, we could refer to bytes as well. So as the number of packets we need to send through the network gets close to the capacity of that network, and that is how many packets it can deliver out, we get congestion. That's the general definition, but for that we need to understand, well, what is the capacity of a network? What's the capacity of our wireless LAN link? A single link, wireless LAN, what would you say the capacity is of your router that I've given you for the assignment? What do you think? 54 megabits per second. That's the capacity of the link. Our Ethernet has a capacity of 100 megabits per second. We call that the data rate. Okay, so that's easy, and that depends upon the link technology, the capacity of a link. Now, what's the capacity of a network with two links? Our router, our source, here's our Ethernet and our wireless LAN. What's the capacity of that path? What's our capacity? Well, the maximum we'd be able to send through from source to destination is limited by the 54 megabit per second link. So that's some indicator of the capacity of the path. Because we cannot send faster than 54 over here, even though we can send 100 this link. From here to here, we're going to be limited by this bottleneck link. So that's some indicator of the capacity. Now, introduce multiple nodes. And make this more complex. This is a router. There are multiple nodes attached here. There may be multiple links coming out. And we start to get a more complex network. With multiple paths to some destination. Now, for our source to reach the destination, how fast can we send? Again, we can look at the individual paths. Okay, on this path, we have some bottleneck. On this path, some bottleneck, and so on. And we can look at the individual paths. But as the network gets larger, it becomes much more complex to work out, well, what is the capacity of an individual path we can work out, but what about the capacity of the network? It's not easy to define what's the capacity of a network because there are many individual links in there. So that's one uncertainty in this definition of congestion. Understanding what is the capacity of our network. There's no easy way to calculate what that is. We said congestion occurs when the packets being transmitted approaches the capacity. Well, if we know the capacity, that's good, but in many cases it's hard to work out what it is. What happens when the capacity is approached? That is, we start sending in at a rate which approaches our capacity. What happens then? That's another thing that we need to look at or understand what happens. Basically, packets are going to be dropped at nodes. Drop packets means the destination will not receive them. From TCP's perspective, if the destination doesn't receive the data, the source will have to retransmit. Retransmissions are bad in terms of throughput and in terms of delay. We want to avoid that. So congestion control in general aims to keep the packets being sent into the network or through the network at a level below which the performance drops dramatically. Below a level that we get congestion. What is that level? How to write that down. We'll see that if we have a capacity of 100, if the sending rate or coming in gets close to 100, we'll start to get congestion. Not necessarily 100. If our capacity is 100 and we start to send in at 90, 95, 96, 97, we can start to get congestion, packet losses. It doesn't have to be the same as the capacity because there's some randomness in there. So in practice, as the input data approaches the capacity, congestion occurs. Therefore, we want to keep the amount coming into the network at a level below some level such that congestion occurs. What is that level? Again, that's complex to know what it is. That is, let's say congestion occurs if the input was 90 or above, then congestion control would try to keep the sending rate below 90. But it's hard to determine what this number is. It varies. So in general, we have this complexity with congestion control, knowing what the capacity is, knowing what level we can send at such that we don't get congestion. What causes congestion? Too many sources trying to send data too fast. If everyone's trying to send into one router at a rate which it cannot handle, packets will be lost at that router. So in IP networks, if this happens, packets are dropped at routers. And from the perspective of TCP, if packets are dropped at routers, packets don't get to the segments don't get to the destination. Lost packets mean larger delay. Retransmissions. Retransmissions mean there are more packets being sent into the network. I'm sending packets in, I have to retransmit, I have to send more packets. Retransmission causes more congestion. More packet losses occur because we're sending more and we get more retransmissions. And if this loop keeps going, the internet will fail. That is, if we get congestion and we've got no way to control, then TCP will have to retransmit packets. Those retransmitted packets will cause more congestion. More packets will be dropped and there'll be more retransmissions. And that keeps going until all of the packets sent through the internet are just retransmissions of the first packet. Nothing gets delivered and we get the failure of our network. So that's why TCP needs some congestion control to avoid this case. Congestion control aims to reduce the rate at which the sources send so that we don't get congestion. Flow control aims to reduce the rate at which the source sends so that we don't overflow the receiver node. Congestion control the rate at which the source sends so that we don't overflow the network, specifically the routers. Last slide. A quick example of a scenario where congestion occurs. Here's a router. There are two hosts connected into the router and two destination hosts, C and D. The router outgoing link, this link, if we look at data going this from left to right, the outgoing link of the router has a capacity of R units. Host A sends packets in at lambda in. So it's got a sending rate of lambda in. That's the sending rate of host A. And same with host B. So sending in at lambda in, sending in at lambda in. If the router has an infinite buffer space, that is, there's no limit in the amount of memory that it has, which means as packets come in, if the input rate approaches R, the output rate, packets will start to be buffered, and as the input rate increases, the time at which those packets are stored in the buffer will increase, because we can only send out at a fixed rate. Lambda out is the throughput of the connection. If we have that scenario, so the lambda out is the rate at which we receive data, a simple plot of performance that characterizes what happens there. The throughput corresponds to the input rate up to some level. That is, increase the input rate, throughput, the output rate will increase, up to a level where our capacity of a link is reached, R is reached. We cannot have a throughput of our application which is greater than the capacity of the link. Here we have two applications. Throughput of one application, if this link has capacity R, the throughput is not going to go above R on 2, because this one gets half and this one gets half, assuming everything's equal. So the lambda out, the maximum it can get is R on 2, half R. That's shown here. No matter if we keep sending more packets, the throughput will be fixed. It cannot go above the capacity. That's okay, that's what we'd like. Increase the sending rate, we increase the throughput up to some limit. That's good. But the problem that arises here is as we increase the sending rate, more packets will be buffered at the router, and the more they are buffered, the longer they have to wait until they're transmitted, the longer the delay. And in general, as we approach the capacity, the delay goes up. And if we have an infinite buffer, we'll get an infinite delay eventually. That is, if we increase the sending rate. This is the bad thing in terms of performance, because delay, we'll see later, leads to, well, if we don't have an infinite buffer, we'll have packet loss. And delay from TCP's perspective means that the packet doesn't arrive on time, we time out and retransmit. So delay, a large delay means packet loss as well. Increasing the sending rate increases the throughput up to some capacity, but in the case of an infinite buffer at the router, will lead to a large increase in the delay of that data transfer. And that's the bad performance there.